Today we're going to continue our discussion of equations. We did equations last time that were either one-step equations, you either multiplied or you added, something like that, or we did two-step equations where you had to multiply and add or subtract and divide. But you only had two steps to solve any of our equations. So we're going to encounter some equations today. They're going to be a little bit more difficult. Some of them that are also not going to end in answers that are whole numbers. I know that always makes me feel a little uncomfortable, like did I make a mistake? Because so often the problems that you're given are sort of contrived and they're created in such a way that you always get a whole number answer and you start to expect that. So as you're working through these problems in your homework tonight, if you're getting fractional answers, don't let that discourage you to think that you've done them wrong. There are some answers that are going to be fractions, okay? So we're going to start with something that we could have started with last time, but the material kind of laid it out to start here instead. Talking about what a solution is. So a solution to an equation is simply a value that makes the equation true. So as you're finding your answers, those answers are solutions if, when you were to plug them back in, it makes the same value on both sides of the equal sign. That's all a solution is. A value that works. And hopefully, if you've solved a problem correctly, that's what you're finding is the solution. So the first thing we're going to do is simply find out if we can make sure that a solution is true. And this is really important because if you get this idea down, it means that even though you don't have a way to check your answers on a test, you can always check your answers. All right? So finding out if something is a solution means taking the value that's given, or the value that you found, and substituting it back in for the variable. So in this case, our variable is x. So if I were to find out or check if this is a solution, I would be plugging in or substituting in the 8 for the x. Okay? So what I'm really doing is I'm trying to figure out if this equal sign really should say equals. That's what we're really doing, okay? I don't really know that it should say it right now. I'm sort of testing it. So if I take this value, 17, what is 6 times 8? 48. And 48 minus 1 is 47. And what do you see happened on this particular example? Yeah, they're not the same. This is not equal, right? So if it's not equal, then it means that the value given, in this case 8, is not a solution. So no, it doesn't work. So we're going to try another one. Same equation. Now I have 6 times 3, which is 18. And 18 minus 1 gives me 17. And what happened this time? They are really actually equal, so yes, it is a solution. So how would you, practically speaking, use this? Well, practically, when you're working especially on a test, but you can practice it on your homework, of course, as well. When you get to the end, like the one I have on the board here, y equals 270, right? You would take your 270 and you put it back in for y. And you would check to make sure that when you actually operate on it the way that it says, it really makes both sides of the equation equal to the same value. And if it did, then you know you got the right answer. And if it doesn't, you know that you need to go back and try and find your mistake. Okay? So we'll try to do this a couple of times along the way just to give you a sense of how to check your own work. But you're going to have a couple of them on your homework too where you're specifically asked to do the directions just like this. Just check it and see if it works or not. So what I'm going to spend the majority of the time doing today is going through just a lot more examples. A lot more, okay? Some of them are more straightforward than others, some of them are more difficult than others, but we're just going to have a variety of things today. So number 3 says we have x plus 23, it's divided by 7, and it equals 3. And when we talked about the equations last time, we talked about working sort of from the outside in. Whatever's the furthest away from x, we start there. So can you tell, is the 23 that's added or the 7 that's divided sort of further away from x? It would be the 7. It's not really written in here, but there is an understood set of parentheses here. All of this is being added together and then divided by 7, right? So that's why the 7 is sort of understood as being further away. So how do I undo multiplication, division by 7? Yeah, I multiply by 7. Yeah. Okay, so the goal is that this reduces over here, leaving me with x plus 23. 7 times 3 is 21. What would I do next? You bet. Subtract the 23 from both sides. And if I do that, what do I get? -2. And let's just check this one to be sure so we can see how that process would work. So I believe this is the right solution. So we're going to evaluate it back in. We're going to substitute it back in for the x. So there's the -2 plus 23 divided by 7. And I want to make sure that it actually equals 3. Sorry. 3. Okay, so now, order of operations, I would add the numerator parts together first. What's -2 times plus 23? 21, right? -2 plus 23. And what is 21 divided by 7? 3. So this checks out, right? It actually worked when I evaluated it back in. Any questions on that one? Okay. Some of the things that we're going to see happen on this lesson that didn't happen on the others is not necessarily that it's more difficult, there's just more involved. There's more steps. Okay, the steps aren't any harder, there's just more of them. And number 4 is an example of that. So if you take a look at number 4, I've got some multiplication of variables times coefficients. I've also got some addition and subtraction. But before I can start with any of that, I've got 2 pieces on the right-hand side that can be combined because they're like terms. What 2 pieces on the right-hand side are like terms? Yeah, the 3y and the -8y. So I've got the -31 still on the left, and then I can combine. What is 3y minus 8y? Right, -5y. And I still have the plus 9. Now the problem looks just like we did in the last lesson. What would I do next? Yeah, I would subtract the 9, moving from the outside in. So what is -31 minus 9? That's -40, right? Because they're both negative signs. Yeah? Equals -5y. And of course, the whole goal was that this added to 0, right? So it's eliminated. It's not there anymore. What would be my next step? Right, divide by -5. Y equals 8. And this will be our last one that we check, but we'll check it just because that way you can see another check, step 1. Okay, so to do this check step, you go back to the original equation. There's -31 equals 3 times 8 plus 9 minus 8 times 8. Lots of 8s in this problem. What's 3 times 8? 24. I have a plus 9. And then what is 8 times 8? 64, right. So I know you can add those, but also you can grab your calculator because there's 3 of them if you'd like. 24 plus 9 minus 64. Is it -31? I've gotten some nods and heads. Good. So -31 on both sides, so it checks out. And again, what that means is that we know we did it right. We got the right answer at the end. It's cool, right? It's like having a back of the book handy all the time, but there's a little work to it instead of just flipping to the back of the book. Okay, so let's do a few more. We won't check all of them at this point or any more of them at this point because I think you know how to check them, which was my goal in showing you that. Taking a look at number 5, what's different about number 5 is that I have numbers, constants, on both sides, and I have a variable on both sides. We haven't had one of those just yet. So what I need is I need all the variables on one side and all the constants on the other side. Josh?
So wouldn't it be easier to take the smaller number, 13y, and subtract it from
That's what I usually do. I usually try and keep my exponents positive. You don't have to. Some people like to always move the variables to the left-hand side. So there's multiple ways as we do these problems that you could move things around. But Josh said the way that I was intending to do as well, which is the 13y to subtract it from both sides. Okay, so let's take that. I have 11. 15y minus 13y would be 2y, and it equals -7. And then again, after that, I'm back at the same part that I was doing in the last lesson. What's next? Subtract 11, you got it. So 2i, good. Yes, you do. So, you got it. Y is -9. Okay. Number 6. Number 6, we see some parentheses, right? So we had that happen last time, but what's new is that not only do we have the parentheses, but we also have a plus 3y after the parentheses. So on this one, we really got to distribute first. There's not another option. I showed you 2 options when we had this happen last time, but now that I've got after the distribution, the addition going on, we do in fact need to distribute. So I'll distribute the 7 through the parentheses. Is that step okay for everyone? Okay. Now, what do you notice on the right-hand side? Yeah, these two have matching variables, right? You bet. So we'll combine those first. You don't have to combine those first. You could add the 35 first. It doesn't matter, but that's what I saw. So then we'll add the 35. What's 25 plus 35? 60. Yep, it is. And then we would divide by 10. Y would equal 6, that's right. Again, could you check it? Could you put the 6 back in for all the y's? Yeah, you definitely could. In the very first equation, don't do it in any of the steps you've done after that, because if you made an error in that step, you won't catch it. All right, you want to put it in the original equation as it was given. Okay, one more, and then I'm going to show you something new. Okay, again, it's not that it is any harder, it's just a lot more of it. And every time that there's a lot more of it, there's a lot more chances to make a mistake. It's just reality. So we've got parentheses going on, and this time they're on both sides. So we're going to distribute them just like we did in the last problem. So what will the left-hand side become after I distribute? Good, and then don't forget the minus 9u after it, okay? And on the right-hand side I have distribution as well. What will that give me? And then minus my 6. Okay, cool. The left-hand side, is there anything that can be simplified, combined?
20u and -9u.
All right, so what is 20u and -9u? 11u, and I still have my minus 25. What can be combined on the right-hand side? -35 and -6. So what is -35 and then minus 6? -41. You guys are doing great. Okay. Next. What do you want to move? We've got a couple options. Somebody give me a... Okay. Do you want to subtract the 5u? Is that right, Preston?
Yes, ma'am.
All right. Sounds good. So if I subtract the 5u, what's 11u minus 5u?
6u.
6u. And then I have minus 25 equals, of course, the 5u's are no longer there. So I've got -41. Okay, somebody else tell me what you would like to do next. Add the 25. Thank you, Jonah. Okay, again, adding the 25s, those pieces are going to eliminate each other. So I have 6u on the left. What is negative 41 plus 25? Good, negative 16. And remember, you've got your calculator if you want to do, double check your subtraction, that's okay. All right, last step. Well, at least we think it might be. What would we do next? Divide by 6. Okay, so dividing by 6 is the point when you probably are going to look at this and go, wait a minute. This does not divide evenly. Did I do it right? Okay, so on this one, I can assure you we did. We did it right. However, we can at least reduce the 16 and the 6, even if I can't turn it into a whole number, right?
So you don't want us to do it in decimal?
This one's going to be a really good example of one that if you do it, it's going to give you a repeating decimal.
That's what you do.
Yeah, we don't want any repeating decimals, okay? So for the most part, if it turns into a terminating decimal, and if you want to write down, 14.5, that's cool. But if you're going to write down 14.3 repeating, like mathematically speaking, that's not a desirable option, okay? It just doesn't work well for putting numbers back into problems. It doesn't work well for checking your solutions. It just doesn't. So on this one, the 16 and the 6 do have something in common, though. What do they have in common? A 2. So if I were to divide them both by 2, now I still have a negative because it is a negative on the front, what would I get? 8 over 3. You got it. Now, maybe not the super most fun thing ever to do to check this one, but could you? You could. You could plug the negative 8 over 3 back into all the u's. It might not be worth your time. That would be a lot of process to check this one, wouldn't it? If you're doing it for homework, sure, that'd be great. If you're doing it on a test, might not really be worth it because it's going to take you a little bit of time, all right? Okay, I want to show you an interesting way when you're dealing with fractions to not have to deal with fractions. So, what our directions actually say are to rewrite this so that it does not have fractions. And it doesn't mean turn them into decimals. That's not what it's telling you to do, okay? So I'd like to show you kind of a trick. It involves some things that you've already learned and maybe just didn't know how to combine in this way before. So we have 2 minus 3 over 4x equals 9 over 10. Now, if you were to do this problem and you were to try to combine the fractions in some sort of way, you'd have to get common denominators, right? We've talked about that before, right? Adding and subtracting fractions, you would need common denominators. So there's 2 ways that we've talked about getting common denominators. One is the least common denominator. And if you can use that, if you see that and work that out well, it keeps your fractions smaller. The numbers are just smaller. If you don't see the least common denominator, you could just multiply your denominators together. You're going to get a little bit bigger numbers to work with, but maybe it's easier for you to work with it that way. It just depends. So I want to show you both of the ways to do this. I'm going to do least common denominators first. It is my preference to do it that way. It's okay if it's not yours, though. So I'd like for you to consider the 4 and the 10. If I were looking at the multiples of 4, the multiples of 10, what's the first one they have in common? 20. 20 is the least common denominator. And if you don't see it, it's okay. I'm going to show you how to do the problem differently in a minute. But what I want to do is I want to multiply every single piece by 20. So I'm going to have 20 times 2 minus 20 times 3 over 4x equals 20 times 9 over 10. Okay? And you're allowed to do that. As long as you operate on every term in the same way in an equation, that is an appropriate legal operation. Okay, we didn't do anything funny. It's totally legit. But the reason that that's super helpful is because every single denominator now is able to be reduced so that it's not necessary. So on the first one, of course, 20 times 2, that's 40. On the second one, though, take a look. The 20 and the 4 are both divisible by 4, right? So what's 20 divided by 4? 5. So this problem becomes 5 times the 3x. It's still minus, but what is 5 times 3x? 15x. No more 4. No more 4, because it reduced with the 20. On the right-hand side, the 20 and the 10 both reduce, leaving me with what? Division, a 2. 20 divided by 10 is 2. So I really only have 2 times 9, which is 18. Now, on this problem, you're done, because all it asked you to do was to eliminate the fractions. And we're going to use this whole eliminate the fractions bit in a moment and then keep solving the problem. But we're just going to respect the fact that the directions don't have that on this one. Now, let me show you another option in case looking for least common denominators is not your favorite thing to do. The other problem that you could, or other way that you could do this is you could just find a common denominator. And the common denominator would simply be multiplying the two denominators together, which would be 40. Okay? It's all right. And I can do the same thing. I can just multiply every factor, or every term by 40. So I have 40 times 2, minus 40 times 3 over 4x equals 40 times 9 over 10. 40 times 2 would be 80. Here again, the 40 and the 4 are going to reduce and give me what? 10. It's division, right? 40 divided by 4 would be 10. So then I have 10 times 3, which would be negative. Well, the negative's already there, but would be 30x. And on the right-hand side, how will the 40 and the 10? It will give me a 4. Again, 40 divided by 10 is 4. And then 4 times 9 is 36. Now, I know those two answers look different, but can you see how they're actually related? Josh, did you say yes? What do you see?
They're basically the exact same, they're just multiplied by 2.
Yeah. The second set of answers is just multiplied. The second box is multiplied by 2 from the first box. You see it now? Yeah. Okay, so they're both perfectly fine answers. You could solve them both from this point, and you would end up with the same solution. So either one is totally fine.
So I
Alyssa.
assume you got the common denominator for 40, but how'd you get the least common denominator?
Yeah, it's a good question. So here's how I think about it. I think about the multiples of 4 because we use small enough numbers, it's easy enough to do that. So I did 4, 8, 12, 16, and once I get to 20, I recognize 20 is divisible by 10. So if I were to make a list of numbers for 10, I would just be looking for the least common, the least one in the list. 10, 20, and they actually match up at 20. There's other ways to do it, but this is how I was thinking of it when I was thinking of it, because the numbers are fairly small, and for the most part, all the numbers we're going to deal with are going to be small. So kind of think back to 3rd grade when you were like learning your multiplication tables, and you go 3, 6, 9, 12, you know, like multiplication tables of 3s like that. That's how I was thinking of it. Okay. Any other questions on that one? Okay, let me show you why that's useful. So we're going to do the least common denominator approach just because for me that works with smaller numbers and I like that. If you were thinking about the multiples of 8 and the multiples of 6, what's the first multiple that they have in common? 24 is it? Yep. And I can multiply each of my terms by 24. So 24 times u over 8 minus 24 times u over 6 equals 24 times 7 over 8. 24 and 8 reduce, leaving me with what? (24 divided by 8 is 3. Thank you. So I have then 3 times my u. It's a u. Yeah. 3 times u, which is 3u. How about the 24 and the 6? How do those reduce? That one's a 4. Yep. So then I have minus 4u over here. And then the 24 and the 8, we already said that those become a 3. And then 3 times 7 is 21. 3u minus 4u would be negative 1u or negative u. And if negative u is equal to 21, and I divide by negative 1, what will u equal? Negative 21. Exactly. Number 10 is a good example of one where the least common denominator and the common denominator are the same. Because I have 5 and 3 and they don't have anything in common. Like 6 and 8 have a 2 in common, right? That's why it happens sooner than just the multiplication of the 2. But this one, it doesn't, so it's just 15. So I have 15 times negative 5 over 3x minus 15 times 4 over 5 equals 15 times 4 over 5x plus 15 times 3. Okay, if I consider the 15 and the 3, I divide them. 15 divided by 3 is 5. Now I have 5 times negative 5x to give me negative 25x. You got it. Next set, 15 divided by 5 is 3. And then I have negative 3 times 4, which is negative 12. Okay, I still have on the next one the same thing, actually, the 15 and the 5. So that's another 3. So 12x, And then 15 times 3. You guys know what that one is? That one is 45. You got it. Okay, I have a little bit more left on this one because the problem had more pieces, more terms to begin with. Okay, so this is one of those cases where if you want to move everything to the left, you'll end up subtracting the x's. You'll subtract the 12x. If you want to keep all of your x's positive, you're going to add the 25x. Which one do you guys want to do? Add the 25x, okay. It would be 37x. So I have negative 12 equals 37x plus 45. Now what? Yeah, subtract the 45. So I have okay, what was it, negative 57 you guys said? Okay, and then what? Divide by 37. And as ugly as it is, that's it. It's negative 57. Whoops, that's terrible looking. Over 37. Okay, I have one example I'm going to skip because I want to make sure I get to this piece right here. Equations can have one solution. In fact, all the problems we've done so far have had one solution. Okay? So you already know what it looks like when an equation has one solution. You start solving it, and in the end you get x equals a number or z equals a number. But sometimes equations have no solutions or they have infinitely many solutions, and I wanted to show you an example of each of those cases so when that happens you'll know what it looks like and what you have expected. So on number 11, I've got parentheses, so I'm going to distribute. I'm going to solve these, attempt to solve these just like normal. There's nothing different about what I'm doing, okay? What is different is what happens next. So what's going to happen next? Don't everybody talk at once. What would be my next step? Subtract a 4x, right? So what happens when I subtract a 4x? Yeah, there's no x's left, right? I end up with an 8 on the left, and I end up with a 6 on the right. And what do you know about that statement? Yeah, they're not equal, right? I mean, 8 does not equal 6. It's never going to work. When that happens, when you end up with two numbers that don't equal each other at the end, it means that there are no solutions. Or you could say 0 solutions if you like that better. Don't say the solution is 0, right? There are 0 solutions. There's not one. Let's try the next one. On the next one, I could actually combine the 3x and the 5x to give me 8x. So I have 8x plus 6. And on the right-hand side, when I distribute, I get 8x plus 6. What do you notice on this one? Those are exactly the same, right? So when it is exactly the same on both sides, that means that I have infinitely many solutions.
I feel like this symbol.
Yeah, you're asking me if you could write this. Is that correct?
Yeah.
Yeah, that's fine.
Okay.
I don't mind. Everybody good? Okay, I know I skipped an example, but it was just another one of the ones where we were doing least common denominator, so it's not a huge deal, okay? All right, we will stop there for today.